This section is on antidifferentiation and indefinite integration, which is basically the same thing. And so here's a couple things to get us started. If you take the derivative of x squared, you get 2x. The derivative of x squared plus 2, 2x. Likewise, x squared minus 5, 2x. Really, x squared plus any constant will give you 2x. And so if we antidifferentiate, that is, find the antiderivative of 2x going the opposite direction, that could be x squared plus any constant. And so this is an integral symbol. So the integral of 2x dx, I'll explain this in a moment. So integral of 2x with respect to x is x squared plus some constant. Could be anything. And so what you get when you antidifferentiate is that a family of functions. There's this parabola, this parabola, this parabola, all these vertically spaced parabolas. So as long as you have the plus c, this is a general solution, and it could be any one of these. Now, as far as notation goes, if we say y is equal to the integral of f of x dx, that's equal to g of x plus c. So f of x is the integrand. You are integrating with respect to x. That's what the dx is, and this also has a graphical component we'll talk about later. That's equal to g of x, which is the antiderivative of f of x, plus c, which is your constant of integration. This is called an indefinite integral. We'll get to definite integrals a couple sections from now. Anytime you have an indefinite integral, when you antidifferentiate it, you will have a constant of integration. The idea here is that the derivative of g is equal to f. So this is the antidifferentiation, of course, differentiation going back the other way. So g of x plus c is a general solution, which yields a family of functions, as I showed on the last page. And if you have an initial condition, by plugging in that initial condition, you can solve for c and get a particular solution, which would yield a specific curve. And we'll look at that in a little bit. So here's using antidifferentiation to solve a sample differential equation. DEQ is an abbreviation for differential equation. It's such a major thing in mathematics that there's whole semester courses in college on it. So we have this differential equation. It's called a differential equation because there's differentials and there's an equal sign. dy dx equals 3x to the fourth. There's only one way we will ever solve these in this class, though, as I said in college, there's a variety of things you need to do for some tougher ones. We're going to do separation of variables. So that means all the x's on one side, all the y's on the other, so we put the dx over to the right. Then you integrate both sides. So you integrate the left, integrate the right. Now, the integral of dy, you could write y plus c. However, when you integrate the right side, there's no reason you have a plus c, so there's no real reason to have two random constants. You just put one of them, so generally we'll put it over here. So the way I got 3x to the fifth over 5 is, when you think of differentiation, constant multiples don't affect anything, so the 3 is just here. And we're antidifferentiating, so we're doing the opposite of the power rule. So rather than multiplying by the exponent and subtracting 1, we divide by the exponent and add 1. So x to the fourth becomes x to the fifth over 5. And so finally we can write it like this. And so another thing to note is that if you're taking the integral of just dy, that's equal to y plus c. One way to realize that is that dy would be the same as y to the 0 dy. So you add 1 to the exponent divided by the exponent. So you add 1 to 0, y to the first over 1. So that's why the integral of dy becomes just y. Okay, now we're doing the integral of 2 dx. You can think of that as 2x to the 0 dx if you prefer. 2 is a constant multiple, doesn't affect anything. Use the power rule. You get 2x to the first over 1 plus c. Once you start to do some of these, I wouldn't expect you to write out every one of these steps. You just quickly go to 2x plus c. Here's another one, integral of a db. So we're integrating the constant a with respect to b. So that's just ab plus c. Integral of dx over x. Now, this is an issue. This is the same as x to the negative 1 dx. You can't use the power rule because you can't divide by 0. So there's a whole chapter almost which is dedicated to just this one particular case because it ends up being so important. Okay, here is a differential equation with an initial condition. So this time we can actually solve for a particular solution. So again, always the same thing. Separate variables, integrate both sides. Integral of dy is y. Integral of 2x dx, it's 2 times x squared over 2 plus c, so the 2's of course will cancel. So now we have y is equal to x squared plus c, which is this general solution. It's a family of parabolas. But we have an initial condition which we can plug in to solve for c. So 2 goes in for y, negative 1 for x. We plug that in, and we solve for c, and we get c is 1. So therefore, y is equal to x squared plus 1 is our particular solution. Now what's going on graphically is that our general solution is this family of parabolas. We want to pick the parabola which goes through negative 1, 2, which turns out to be y is equal to x squared plus 1. So even in this rudimentary drawing, it still makes sense that this particular one with the y-intercept of 1 would go through negative 1, 2, as opposed, of course, to 1 down over here. Now, as far as antidifferentiating, it is just the opposite of differentiating. So the integral of cosine x dx is equal to sine x plus c, because the derivative with respect to x of sine x is equal to cosine x. Or you could say the integral of x cubed dx is equal to 1/4 x to the 4th plus c. Again, you're just using the opposite of the rules you would have learned in the previous chapter, or actually chapter 2 when you first learned differentiation. So now let's look at some more sample problems. Okay, in this one, integral of x squared minus 2x plus 3. As we'll see later, integrals are sort of based on limits, and with limits you can separate things and evaluate them individually. You can do the same thing with derivatives. So basically you can integrate each piece individually. So this piece becomes 1/3 x cubed, or x cubed over 3. This piece becomes minus 2 times x squared over 2. This piece becomes 3x, and again we have a plus c. Don't forget the plus c, and we can just simplify it a little bit to get to here. So you can integrate term by term. This is written inconveniently, and in the same way with differentiation, radicals and fractions are inconvenient. It's the same thing with integration, and so we write it using rational exponents. So again, just apply the power rule. Add 1 to the exponent and divide by the exponent. So it's x to the 3/2 over 3/2 plus a half. Add 1 to negative a half, and you get x to the half divided by a half plus c, of course. And then divided by 3/2 is like multiplying by 2/3. You can cancel out some stuff over here. And so there's your antiderivative. Also known as your indefinite integral. Okay, same idea here. Add 1 to the exponent, divide by the exponent. Integral of 1 is x plus c, and then divided by 7/4 is like multiplying by 4/7. Okay, more examples. For this one, you have to distribute first. You can't integrate the way it is now. So you've got to multiply the whole thing out, FOIL it, and then integrate term by term, and you get to here. For this integrand, we're integrating with respect to theta, so you just use power rule. So we have 1/3 theta cubed. Over here, you have to recall the derivative of tangent secant squared. Therefore, the antiderivative of secant squared is tangent, and you have plus c again. More tricks. We distribute secant, and in distributing secant, now we have this integral. Now the integral of secant tangent is secant, because if you recall, the derivative of secant is secant tangent. Because the derivative of tangent is secant squared, the integral of secant squared is tangent, and then of course plus c. For this one here, Pythagorean identity, 1 minus sine squared is equal to cosine squared. So we can rewrite that as secant tangent, because sine over cosine is tangent. You've got 1 over cosine left over, which is secant. And again, the integral of that is secant x plus c. Okay, this one is a little bit more involved. We know what the second derivative is. We have an initial condition for the first derivative, an initial condition for the function. So we want to get all the way down to just where we have f of x is equal to something. So f prime of x is the integral of f double prime. So that's the first thing, is we integrate f double prime. We have 1/3 x cubed plus c1. Now we're going to have a couple constants of integration, even though they're kind of random at the beginning. You can't call them the same c, so that's why I'm using a subscript. So f prime is 1/3 x cubed plus c1. We use this initial condition. So we plug in 6 for f prime, we plug in 0 for x, and we solve for c1. So we get c1 is 6. So therefore f prime of x, 1/3 x cubed plus 6. Now we repeat the process. We integrate f prime in order to get f. Integrate all this. Antiderivative of this over here. 6 becomes 6x plus c2. Then to solve for c2, we plug in this initial condition. And once again, we can get our c2. And then finally, we get down to the solution to that differential equation. Okay, last thing is more graphical. We have spent some time before drawing f prime on f. Drawing f on f prime is a little bit trickier, doing the reverse. Now again, because you can get a family of functions, there's many possible answers which can be displaced vertically. We'll just do a couple. So first of all, f prime is a line, so if you antidifferentiate it, you should expect to get a parabola. Another thing is the derivative goes from negative to positive, and so by the first derivative test, negative to positive implies a minimum. And so that would mean you might want to draw something like this, but of course it could be up here, could be vertically displaced, you don't really know, but that sort of curve. Now for this one, I'm increasing faster and faster, and I'm always positive, so that means you don't know where you start. You could start down here, but you know you're always increasing, and you're increasing faster and faster. So for all I know, maybe f starts up here and goes up. You really don't know. Here you're decreasing very quickly and almost flattening out. So if you're decreasing very quickly, and you're not decreasing. You're increasing, but not as fast. So we could be starting out increasing very fast and then almost flattening out. The derivative here is positive, therefore f should be increasing. But derivative is still positive, so you shouldn't be increasing as fast.